Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing on with our discussion about hypothesis testing and confidence intervals. We're going to be changing gears a little bit from what we've been doing in the last few videos. If you recall, so far we've sort of discussed 3 different hypothesis tests and 3 different confidence intervals. Now, the sort of linking theme of all 3 of those procedures, either the hypothesis test or the confidence intervals, has been that everything in our discussion so far has always been about quantitative data. That meant we've been doing a lot with talking about averages and standard deviations, whether it's been a single sample of quantitative data, 2 separate samples of quantitative data, or 2 matched samples of quantitative data. Now we're going to begin changing gears and talking about categorical data and how to work with that sort of information. So to do this, we're going to be changing our minds away from thinking about things like averages and standard deviations, and instead thinking about mostly in terms of percentages. So we're going to start off with sort of the simplest case, what to do when you have a single sample of categorical data. So we're going to talk about this as what is called the one sample proportion hypothesis test. So this hypothesis test is used when you have a single sample of binomial or Boolean categorical data that you want to compare against a known or assumed percentage. So the first thing we want to sort of call attention to is this little restriction here. Right now, we're going to be talking about a very specific type of categorical data. We're going to be talking about binomial or Boolean categorical data. Now, if you remember way back to the beginning of our class when we first introduced the sort of different types of categorical variables, Boolean or binomial was just a fancy sort of name for categorical variables that only have 2 options, that only have 2 categories. So right now, this hypothesis test is going to be restricted to working on variables like that. Now remember, there are some variables out there that are naturally binomial or Boolean, such as answering a yes or no question, do you support a particular law, or do you plan on voting for a particular candidate? Those are naturally Boolean because you have to say yes or no. There are other things that might not be naturally Boolean, but we can phrase the question to become Boolean. Remember, we gave the example of talking about like something like political affiliation. Well, if you think about the US, there's many, many different types of political affiliation. Democrat, Republican, Independent, Libertarian, Socialist, so on and so on, right? But if we restrict that to saying, is this person a Democrat, yes or no, then we can analyze that from a sort of Boolean perspective. So right now, this sort of hypothesis test is going to be restricted to where we have a yes-no success-failure sort of situation for our categorical data. Notice that this is also very similar to how we talked about the one sample mean procedure, right? We're going to be taking our single sample of categorical data and comparing it against a known or assumed percentage. Just like how when we were doing the one sample mean procedure, we'd have to compare it against a known or assumed average. All right. It's going to have the same structure in the sense that there's going to be 5 steps here. And let's talk about what the hypotheses are going to look like. Well, notationally, we're going to change things a little bit. We're not going to use mu because that represents an average. Instead, we're going to be just using the variable p to represent the percentage or the proportion. So our null hypothesis is going to be some assumed value for that proportion or percentage. So this right here is going to correspond to that known or assumed percentage. And just as standard, for the alternate, we can think that that percentage has increased, decreased, or is simply different or has changed from the original value. So once again, when we are setting up these hypotheses, there's going to be 2 things that are going to be sort of necessary. We're going to have to figure out the value that's going to go there, and then also figure out the correct inequality. When we were doing these sort of mean procedures, we often reference these 2 as one-sided, and this guy is 2-sided. We're going to continue that, but we're going to be a little bit more specific about these. If we decide to use a greater than, we're going to specifically call that right-sided, which should make sense because things that are larger are on the right. If we decide to use a less than, we're going to call that a left-sided test. And we're going to stick with the exact same terminology. If we decide to use a not equals to, we will call that a 2-sided for that. So when we were doing our quantitative analyses, it didn't really matter if things were right or left-sided, but we'll see that in this case it does matter a little bit. So instead of just calling things one-sided, we will be more specific now and call them right or left-sided. Of course, if it's not equals to, we'll still call it 2-sided. All right, we'll have a set of conditions. First two conditions should look identical to the conditions we've been doing beforehand. The sample must be random and representative, and the sample size must be less than 5% of the population size. To be honest, these two conditions you guys are going to see a lot anytime we're introducing a new procedure. That third condition is going to change a little bit, though. The third condition in the past used to be that the data was approximately normal, or that the sample size was greater than or equal to 30. Obviously, that idea of normality doesn't make any sense here because we're not working with quantitative data anymore. We're working with categorical data. So we need a slightly different condition. This condition, though, shouldn't look too unfamiliar. We actually used this condition before when you guys learned the normal approximation to the binomial, and it's actually the exact same condition. What you need to check here is you need to check that your sample size times your null hypothesis times 1 minus the null hypothesis has to be greater than or equal to 10. So just keep in mind that that p that is referenced in here is exactly what's coming from that null hypothesis up there. All right, let's go ahead and talk about the test statistic. First thing that should stand out to you is that the test statistic here isn't going to be a t-test statistic. Instead, it's going to be back to our original type of distribution, the actual normal distribution. So it'll be a z-test statistic. Why is it a z-test statistic and not a t-test statistic this time? Well, it's a z-test statistic here because remember, we use the t-distribution because we sort of commented that in our discussion of the central limit theorem, we're assuming we would have access to the population standard deviation. But in reality, we didn't have access to that, and we had to estimate using the sample standard deviation. Well, that introduced some extra variability, and the t-distribution was exactly the right distribution that had enough extra spread to mimic that extra variation. Well, when we're working with categorical data, there is no standard deviation. Population, sample, that's a concept that doesn't make sense when we're talking about categorical data. So there's no need to do that estimate, so there's no need for this to be a t-test statistic. So instead, things are a little bit simpler, and we're back to our normal, pardon the pun, our normal distribution, the z-test statistic here. What are these other things in here? Well, there's three things that we need to know to plug into this. We need to know p hat. Sorry, that should be a little caret on top, so p hat. This is what we call the sample proportion, and this is going to be found by taking the number of successes in our data and dividing by n. So the sample proportion is, in other words, the proportion that you see in your data. So you'll count up how many successes, how many people landed in the success category, divided by your overall sample size. P, of course, is the notation for our null hypothesis, and then n, of course, is your sample size. So a little bit simpler here. There's only three things you need to know to plug into this sort of equation. You need to know that sample proportion, the null hypothesis, and the sample size. One thing that you should notice is that the entire denominator of this, the p's down here, do correspond to the null hypothesis. They do not correspond to the sample proportion. The sample proportion only shows up right there. In general, this test statistic overall should seem very sort of familiar. As always, the numerator is measuring how different your sample is from your null hypothesis, and then the denominator is giving you sort of a measure of how much variability we expect in our data. All right, when you go to step 4 to calculate the p-value, because your test statistic is going to be a z-test statistic, you won't need to use table C. Instead, you'll be using your old table A and the direction of the alternate hypothesis. That's why it's so important that when you're doing these proportional procedures, you identify right-sided or left-sided, so that when you go to get your p-value from table A, you know, do you need to look to the left or to the right? And as we know on table A, what you find from the table is always on the left-hand side. So if you're doing a right-sided test, you're going to have to do 1 minus that value, just like we did when we were originally learning how to calculate things using the normal distribution. So we'll see an example of that in just a little bit, but just keep in mind your p-value now will be from table A. Finally, the conclusion, this part, no matter how many hypothesis tests we cover in this class, will never change. If the p-value is small, if it's less than alpha, we will be rejecting HO, which means we have significant evidence for HA. If the p-value is larger than alpha, we will be failing to reject HO, which means we have no evidence for HA. All right, let's go ahead and talk about the corresponding confidence interval for this type of data. So this is the one sample proportion confidence interval. So this is the sort of related procedure. This is again used when you have a single sample of binomial or Boolean categorical data that you want to use to estimate an unknown population percentage. So again, as always, the hypothesis test is there to sort of help you identify if the data you have is evidence for some sort of claim, whereas the confidence interval is really there to help you build an estimate. So the conditions for the confidence interval, it is a little special here. This is the one time in our course where the conditions for the confidence interval are a little bit different than the conditions for the hypothesis test. You'll notice here that it says that conditions 1 and 2 are the same as the one sample proportion hypothesis test. That means that the data still has to be random and representative, and this means that the sample size still has to be less than 5% of the population size. Condition 3 is a little bit different, and let's talk a little bit about why condition 3 has to be a little bit different. If we go back to the hypothesis test, remember condition 3 is this NP1 minus P has to be greater than or equal to 10. Notice that that condition is based on your null hypothesis. Well, when you're doing a confidence interval, there's no hypotheses. It's a confidence interval. It's a completely different procedure. So condition 3 must be something different because we can't reference a hypothesis if there isn't a hypothesis. So condition 3 is a little bit more based directly on the data. What condition 3 says is that you must have at least 10 observed successes and at least 10 observed failures in your data. What that basically means is that for whatever variable you're studying, remember we have the assumption that it's binomial or Boolean, so people either fall into the success category or the failure category. What we're basically saying in this condition is that we have to make sure that we have at least 10 individuals who we counted as successes and at least 10 individuals who we counted as failures. In other words, we need to observe in our data at least 10 successes and at least 10 failures. Then the construction is pretty standard. We're going to be using p hat, our sample proportion, as our point estimate. So this right here will be your point estimate. And this part here, this z star square root p hat 1 minus p hat divided by n, that will be your margin of error. To plug into this formula, what you'll need to know is you'll of course need to know the p hat, which is your sample proportion. And like we said, that is your number of successes divided by n. Notice I'm starting to abbreviate here. Anytime you guys see S and F, you should recognize that when you're talking especially about sort of categorical data, S is going to reference successes and F is going to represent failures. So the sample proportion is S divided by n. Of course, you'll need to know n, which is your sample size. And then you will also need to know this Z star. Now, Z star actually is found on table C. It's actually the very bottom row of table C. So what you will be doing is you'll find that Z star row and you'll find your confidence level across the top and you'll intersect those and that'll give you your Z star. And that will actually happen on table C. So while we use table A to calculate the p-value, we still use table C, even though it's a Z test statistic, to actually find that Z star there. Now, let's just go take a quick look at that table C there, right, just to make sure we can see where this is located. So if you go on to table C, remember, normally we would find these degrees of freedom. At the very bottom, though, as the degrees of freedom go larger and larger, you will see the Z star at the bottom. This actually relates to the comment that we made that the normal distribution is really the t distribution with an infinite degree of freedom. So this Z star is what you'll be using. So you'll intersect that Z star with your confidence level. So if you want 95% confidence in Z star, you would use that value right there. Notice that that does mean that when building a one sample proportion confidence interval, there is no need to use degrees of freedom because you're just always going to be using that Z star. Alrighty, so there we go, right? Now we know how to build a one sample proportion confidence interval for estimating an unknown population percentage. We're going to do several examples of this in later videos, but let's get in and look at one example in this one just to make sure we're comfortable with all the stuff that we've laid out so far. All right, so this is an example that uses one of, I think, my favorite sort of data sets. It was a study done by the LA Times about American adults and their knowledge of sort of terminology about technology. The one that we're going to be using is as follows. So, according to a study done by the LA Times in 2014, 18% of American adults believe that blue ray is a type of marine animal. So 18% of American adults, when they were asked this question, thought that blue ray wasn't a form of sort of like a DVD or like a way of digitally carrying data. Instead, they believed that it was a marine animal. This was a little bit scary. There were even some scarier ones. 12% of American adults actually believed that HTML was a form of an STD, and 26% of American adults believed that MP3 was one of the robots from Star Wars. So a little bit scary here, because the point of this whole study, not just to be sort of funny here, but was to really see that even though technology sort of permeates our culture, people's use and understanding of the terminology is a little shakier. So this study was done in 2014. 18% of American adults believe that blue ray is a type of marine animal. We want to study if this percentage has decreased. Notice already, just in the sort of phrasing of this question, we see things like the percentage or percentage written out in words. This is all tip-offs that we're talking about categorical information here. So to study this, you randomly select 200 adults from across the country and find that 31 of them believe that blue ray is a marine animal. So we're going to do two things with this. We're going to carry out an appropriate hypothesis test to test the claim that the percentage of American adults who believe that blue ray is a type of marine animal has decreased since 2014. In other words, we're basically claiming that people have gotten a little bit more literate about terminology and technology. And then we're going to build a 95% confidence interval for the percentage of American adults that believe blue ray is a type of marine animal. All right, so let's jump right in and talk about A here. What type of hypothesis test is this going to be? Well, as you can sort of see here, we have our single sample of 200 adults. We're studying something that is a binomial or Boolean variable. Do you believe blue ray is a marine animal? Yes or no. And we've got a known or assumed percentage back from 2014 to compare it against. So this is going to be a one sample proportion hypothesis test. It's one sample Boolean data versus known/assumed percentage. So that's exactly what this is designed for, right? We've got our one sample of Boolean data, those 200 people that we interviewed, and we've got a known or assumed percentage. So let's go ahead and set this up then. So to start with, we're going to have to set up our hypotheses. So for the hypotheses here, we know that we're going to have an HO and an HA. Because we're talking about a proportion here, the form of the null is going to be P equals something, and the alternate is going to be P, some inequality, and that same value. First, we need to fill in this value. Since we're talking about a assumed percentage, we're going to be using that one from 2014, which is 18%. It is totally fine to write it as 18% here and here, but as we know later on when we need to actually use this value, anytime you need to do arithmetic with a percentage, you have to use it as a decimal. So it might just be easier, instead of writing it as 18% here, to write this in decimal form, 0.18 and 0.18. Then we have to figure out the appropriate inequality to use here. We look at our claim. We are trying to see that blue ray, that the percentage of American adults who believe that blue ray is a type of marine animal has decreased. So we will be using our less than here, and this will be a left-sided test. Okay, so our hypotheses are set. Let's go ahead and talk about our conditions. So for our conditions here, the first thing we need is it to be random and representative. That has been stated right in the text as usual, so we're good there. Then we need to look at our sample size and make sure that it's small compared to our population size, less than 5%. Well, our population here is American adults, and there's certainly lots of those, so lots of American adults, so we're all good there. And then for condition 3, we need to actually check this. We need to take NP1 minus P and multiply those together. So the N in this case is 200. The P, the null hypothesis, was 0.18. And then we'll have to do 1 minus 0.18. So make sure when you type this into your calculator, you go ahead and you use those parentheses just as written there. So we'll do 200 times 0.18 times 1 minus 0.18. And when we get that, looks like you should get 29.52, which is greater than or equal to 10, so we're all good there. So we're always going to be trying to get a value that is greater than or equal to 10 there. 10 is, again, just one of those statistical conventions, right? It's a agreed upon value, which this needs to be over for this third condition to be met. All right, let's go ahead and look at our test statistic then. For our test statistic, we're going to be using z. Z equals p hat minus p over the square root p1 minus p divided by n. So we need to know three things here, p hat, p, and n. So what do we know so far? Well, we've already talked about this guy, that p equals, that is our null hypothesis. So we've got our 0.18. Our sample size, we've already mentioned that as well. We've already used it, in fact, it's 200. And now we need to get our sample proportion. So let's go back and look at our data. We saw that 31 of the people here believe that Blu-ray is a marine animal. And that was the variable that we're sort of looking at. So those are the people that we consider successes. So we had 31 successes out of the 200 people that we talked to. So our sample proportion would be 31 divided by 200. 31 divided by 200, we want to get that as a decimal there. So let's go ahead and do that. And we should get that will come out as 0.155. If you think about that as a percentage, what that's saying is that in our sample, 15.5% of the adults that we talked to said that Blu-ray is a marine animal. Now what we're trying to figure out is that 15.5% low enough compared to the 18% to really believe that there's been some fundamental change, or is that well within the normal variation, so it's not going to be enough evidence? Well, let's go ahead and find out by calculating this. So we're going to have 0.155 minus 0.18 divided by the square root, 0.18, 1 minus 0.18 divided by 200. So we plugged in all of our stuff there. As always, let's go ahead and do these computations on top and bottom separately. So we'll go ahead and just pull this thing up there. So up top, right, we should be using our calculator to take 0.155 minus 0.18. And it looks like up top, we should get minus 0.025, and then in the denominator, again, you can just type that directly in as long as you make use of those parentheses. So parentheses 0.18 times parentheses 1 minus 0.18, close those up, divide by 200, and you should get, once you put all that in, 0.027. Now you will notice that I'm keeping three decimal places with pretty much everything I'm doing right now. That is a very good idea here because everything we're going to be working on for the next while in our class is going to be about percentages for categorical variables. And percentages, when you convert them into decimals, naturally have to be very small numbers. They have to be between sort of 0 and 1. So you want to really make sure you keep at least three decimal places while doing this to preserve some additional accuracy. So we can actually go ahead and finish this up, negative 0.025 divided by 0.027. And it looks like our z-score here should be approximately negative 0.93. Now you will notice that the z-score I only keep two decimal places on because we're going to look that up on table A. And remember, on table A, you only have two decimal places of accuracy. So here at the very end, it is okay to go ahead and round to two decimal places. All right, now step 4, our p-value. We can actually go ahead and diagram this out a little bit more before we jump onto our table. So we're going to draw our sort of normal distribution since we know we're following that distribution because we have a z-test statistic. The middle you can imagine is sort of the null hypothesis, and we just figured out our z-value is negative 0.93. So we are actually located somewhere over here. Z equals negative 0.93. Now, we are doing a left-sided test, so what we're going to be doing is shading in all this stuff over here to the left, and that right there, whatever that area is, that is our p-value. So our p-value corresponds to the probability that we would get results as or more extreme, assuming that null hypothesis is true. So it corresponds to that area there. So we can get that by looking that up on table A. So let's go ahead and do that. Table A. So we're looking up that negative 0.93. So there's negative 0.9 right there, and 0.91, 0.92, 0.93. So there's our value, 0.1762. So we get 0.1762. As always, we know that that's the stuff to the left. So the stuff that way is 0.1762. And notice that that does correspond with our shaded area. So we can conclude in this case that our p-value is equal to 0.1762. Notice that this is sort of nicer than when you guys were learning about how to do quantitative procedures. With quantitative procedures, because of the limitation of table C, we only got a range for the p-value. Now we're getting an actual specific value for the p-value. So that makes things a little bit easier. We actually get a single value for it. All right, let's go ahead and make our conclusion then. For our conclusion, we need to take this p-value and compare it against alpha equals 0.05. Obviously, this is much larger than 0.05. This is like, as a percentage, 17.6%. This is 5%, so the p-value is larger. Whenever the p-value is larger, we make that conclusion of fail to reject HO. So in other words, we have no reason to throw this guy out. So we'd say that there is no evidence for our claim. No evidence that the percentage of American adults who believe Blu-ray is a marine animal has decreased since 2014. So what we've just found here is that there's no evidence to support that that percentage of Americans who believe Blu-ray is a marine animal has decreased since 2014. Obviously, in our little sample of 200 people, the percentage was a bit lower, but it wasn't low enough to really believe that there's been some fundamental change. All right, let's go ahead and try the other procedure we talked about. Let's build a confidence interval for the percentage of American adults that believe Blu-ray is a marine animal. So we're going to use our data here to sort of construct a range of believable percentages. And we expect 18% to be in that range since we were unable to throw out the null hypothesis of 18%. But let's go ahead and build that confidence interval. So we'll give ourselves a little bit of an extra page here. All right, so this will be part B, right? This is going to be a one sample proportion confidence interval. Why is that? Because we want to estimate unknown percentage, right? So when you want to estimate a single unknown percentage, that's going to be a one sample proportion confidence interval. So let's go ahead and talk about the conditions. For the conditions, well, 1 and 2, those have already been checked. So we're all good with that. Unfortunately, though, condition 3, as we talked about, is a little bit different. It is not based on that NP1 minus P being greater than or equal to 10. Instead, we need to check the successes and failures. So let's think about the successes. How many successes did we have? Well, if we look back in our data, right, we know that we had 31 people say that Blu-ray was a marine animal. So we had 31 successes. That means in our data, we observed 31 people counting as a success in our categorical variable. That is greater than or equal to 10, so we're all good with that. We also need to check the same for the failures. How many failures did we have? Well, the data doesn't immediately give us that. It tells us that there were 31 people that believed this. But remember, we can use the fact that things here are Boolean. There's only two options. So since we talked to 200 people and 31 said that Blu-ray is a marine animal, we can figure out the ones that said that it was not a marine animal by just simply doing 200 minus 31, which is going to be 169. So we can say that there were 169 failures. That is greater than or equal to 10 as well, so we're all good. So the conditions are met. This is the one confidence interval, which if you do it as a follow-up, you do need to check one extra condition, because that condition 3 is different. Now we can go into the construction. So for the construction, our formula is going to be that p hat plus or minus z star square root p hat 1 minus p hat over n. And we've got 3 things that we need to know there. Well, this p-hat, we already calculated that. That was 31 out of 200, right? It's the number of successes divided by the sample size, and we know that that's going to come out as 0.155. And, of course, our sample size was 200. And to find the z star, well, remember what we want to do there is we want to take our confidence level, 95% confidence, and we're going to intersect that with z star. And remember, this is going to happen on table C. So let's go ahead and do that, 95% and z star. So if we go do that on table C here, 95%, I'll zoom out a little bit, 95% z star, that gives us this as 1.960. Now, one thing that you guys can sort of make use of is that since there is no degrees of freedom, if in a later example or on a quiz or something, or the suggested exercises as you guys are working, if you need to do a 95% confidence interval for some sort of proportion, well, you're going to use the exact same z star because there's no degrees of freedom. So you can sort of remember, z star for 95% is 1.960. And you might want to do that for other ones that we commonly use, like 90% and 99%, so you don't even need to look at the table. Obviously, it's not hard to look at the table, but if you want, you can know, since there's no degrees of freedom, that z star is never going to change if you use the same confidence. So we've got 1.960 here. So let's go ahead and do that. We've got 1.960. 1.960. So let's go ahead then and plug all that stuff in. So we have 0.155 plus or minus 1.960 square root 0.155 parentheses 1 minus 0.155 and then divided by 200. As always, go ahead and type in this margin of error first. So we'll be putting in 1.960 times the square root 0.155 times parentheses 1 minus 0.155 divided by 200. And looks like when we do that, we should get 0.155 plus or minus, we'll keep 3 decimals again, 0.050. Then, as always, do your subtraction first. So when you do that subtraction, you should get 0.105. And when you do the addition, you should get 0.205. So we can say we are 95% confident that between, and might be easier to interpret these as percentages, so between 10.5% and 20.5% of American adults believe blue ray is a marine animal. So we believe anywhere from about 10.5% of the population to 20.5% of the population believe that blue ray is a marine animal. Notice at 18%, what we tested as our null hypothesis in part A is right in that range, which is why we were unable to throw it out. That's why we failed to reject HO. That's why we were unable to find evidence that the percentage has dropped below 18%, because that was something we considered believable according to our confidence interval. In our next video, we'll continue on with some additional examples, running through more cases of the one sample proportion hypothesis test and the one sample proportion confidence interval.